Hello and welcome to the channel Understanding.Concepts.Of.Physics. Today we are here to discuss something called as damped simple harmonic motion. We have been discussing about simple harmonic motion since past few videos, and we have never considered friction or air resistance or the medium's resistance to simple harmonic motion. In this video, in this topic, we are going to discuss about the resistance offered by the medium. And we all know that when a spring oscillates, if it is going back and forth, then definitely at some point of time it is going to come to a halt. But as of now, up till now, we have understood that if there is no air resistance and friction, this is going to oscillate again and again till infinity. But if there is air resistance and friction, how it is going to react? So we know that if the oscillations of gradually decreasing amplitude, when the oscillations are having a gradually decreasing amplitude, it is called as the damped simple harmonic motion. So damped simple harmonic motion is nothing but oscillations with gradually decreasing amplitude. Okay, so this is the definition for damped simple harmonic motion. Now we'll see the diagram in order to derive the differential equation of damped simple harmonic motion. So just keep on watching where my pointer works. This is the rigid support. We have fixed a spring with a rigid support, and there is this mass M attached in the spring on the other side, and there is this one rod which is connected to a vane. Vane is basically kind of a plate, and we have this container in which this plate has been kept, and we have some medium. So initially we can assume that the medium is air. So the damping actually depends on the medium. That is one of the factors. So if there was nothing in this, let's say if I consider that there is nothing in this, if there is only air, then as I start to move this block up and down, this vane is going to move up and down, back and forth, to the positive extreme, to the negative extreme, and this will be the mean position. Now the reason why it is happening is because of this spring, but because there is air here all around, the damping is pretty less and it is going to vibrate for a larger time. But suppose if I fill with some medium, here, some water, let's say water, then what is going to happen here is the oscillation is going to stop at an earlier time. It is not going to sustain for a larger duration. And suppose if this was not water, this was oil, then oscillation will die very soon. And if this is glycerin, it is going to die much sooner. So the damping is actually depending upon one, that is the medium, and it also depends upon how fast it is coming. That means the damping also depends on the velocity as well. So if something is coming very fast, let's say if I pull this vane till this point, now when it is going to come at this point, it is going to be the fastest at this mean position, and the faster it is, the more damping it will experience and the more quicker it is going to stop. It is as good as when you run on a windy beach. When you run on a windy beach and wind is against you, wind is against your direction of motion, then you experience a large amount of resistive force. So basically damping depends upon how fast things are moving, so it depends on velocity as well. Okay, so the faster you move in a car or a bike, the more air resistance you are going to experience and more fuel you are going to burn. So that way it works. So whatever we have assumed here, I have written that in words. This is in the statement of consider, and then we are going to see how to derive that equation. So here, gravitational force acting on the vane is Fg is equal to mg, and the restoring force by the spring is equal to Fr is equal to minus kx. So gravitational force is acting downwards, and the restoring force is acting on the vane because of this spring is Fr, which is the restoring force, minus kx. So these are the two forces, and then there is something called as damping force applied by the medium. Now the damping force depends, as I have discussed, it depends on velocity. Higher the velocity, higher the damping force. Lower the velocity, lower the damping force, and it also depends on the medium. So I am writing that in an equation. Fd is directly proportional to minus of V. Now again, why this minus have come? Now when suppose this vane is in this position as of now, and the vane is coming upwards, that means the velocity is pointing upwards, but the damping is going to try to stop it. So damping force is pointing downwards. So, and that goes other way as well. Suppose if the vane is at this position and it is coming down, so the velocity is acting down, so damping is going to stop it, and damping will be against the motion of that vane. So the damping force is opposite to the velocity. That's the reason why we use a minus sign over here. Then we apply a constant term, and that constant is B, and this is what is called as the damping constant. So B is called as a damping constant. If you just move V on the other side, you get B is equal to Ft by V. Now you will say, sir, where is the minus sign? Minus sign is just showing the symbol that force of damping and velocity is in the opposite direction. Yes, we will get a minus sign over here, but if you take the modulus of that, the minus sign is going to go off. So, and the unit, now Newton, force is in Newton, velocity is in meter per second. So the second goes up, so I'll get Newton second per meter. So this is my unit of B. Dimension would be m1t minus 1. Again, you can always work on L1 m1t minus 2 is the dimension for force. Velocity is L1t minus 1. You can L1 and L1 gets cut. T minus 1 goes up. T plus 1 minus 2 plus 1 will give me minus 1. So this is what the dimension is. So that's what I have mentioned. Negative sign indicates that damping force is against the velocity. Now I'll find out the net force. So net force is equal to damping force plus restoring force plus gravitational force. So Fg is negligibly small. Now you know Fg is not small, but in comparison to damping and restoring force, the value of Fg would be much smaller. That's the reason why we are going to ignore Fg. So we are going to ignore Fg because the Fg value in comparison to damping and restoring is much lower. So Fnet is equal to Fd plus Fr, and net force is mass into acceleration. Force of damping is minus of Bv. Force of restoration is minus of Kx. We'll move this on the other side. Bv comes here, Kx comes here. So minus will become plus, minus will become plus. So I'll get mass into acceleration plus Bv plus Kx is equal to 0. Now acceleration. Now what is acceleration? Acceleration is basically the double derivative of displacement with respect to time. So wherever there was an acceleration, I have replaced with double derivative of displacement. Velocity is the single derivative of displacement, and x is the only displacement, so x is kept as x. Now this is what is called as the equation of differential equation. It's called as the differential equation of damped simple harmonic motion. And if you see, when we were discussing without friction, without air resistance, without damping, this term was not there. So my equation was md square x by dt square plus kx is equal to 0. This was that equation. But because there is damping, this term has come in the middle. Then we can solve the differential equation for this, but the solution for differential equation is you are not supposed to solve it in any +2 grades. Maybe in some boards it might be there, but in the major boards of India, the differential equation for this one is not required to solve. So you just have to remember the solution of that. So the solution of damped simple harmonic motion, yes, definitely if you are well versed with the differential equation, yes, you can solve this differential equation and get to this point. But majorly the boards are not demanding the solution for damped simple harmonic motion. So I'm writing this equation directly, so you can just by heart it in case if your board does not demand. In case your board demands, you need to solve that. So x is equal to a e raised to minus bt by 2m cos of omega dash t plus phi. So this is the solution of that damped simple harmonic motion same differential equation, wherein if you see wherever there is this term, there is the number or the coefficient of the cos, like whatever the things is before cos or sine, is called as an amplitude. So a e raised to minus bt by 2m is an amplitude, and if you see b is a constant, f2 is a constant, m is a constant, and only variable is t, and that too is a negative sign. So bt is this is an amplitude which is an exponential decreasing with respect to time. Now a is a constant, again a is a constant, b is a constant, 2 is a constant, m is a constant, and t is a variable. E is called as an exponential constant, and E is exponential constant, and the value for E is equal to 2.718182, and it keeps on going. It's an irrational number. It is a number which keeps on reoccurring in mathematics, and that's the reason why we use it. So there will be a lot of details about exponential constant in mathematics, but we are not into that course of studying exponential constant. You can just see that k as how pi, that is 3.14, is a number which keeps on reoccurring whenever we divide a circumference, whenever we divide any circumference of a circle with its diameter, you always get 3.14. How big the circle is, how small the circle is, anytime you divide the circumference by this diameter and you will get this number again and again. So similar manner, in math you experience this number again and again and again, and that's why we denote this number, a very special number, to be as exponential constant. And because it is depending on negative side of t, it is an exponentially decreasing graph, so the graph will come decreasing. Omega dash is an angular frequency, and omega dash is equal to square root of k by m minus b by 2m the whole square. This is the omega dash ka value. Phi is the initial phase angle, as we have discussed in the previous videos. Time period for time period it's very simple. Omega is equal to 2 pi by t, so t would be equal to 2 pi by omega. So just replace the value of omega from here and you get the time period ka value. So this is just a division by 2 pi, so 2 pi divided by omega dash is what we get. Of course I have not written frequency. You can just invert the time period and you will get everything ulta. So you can just find out the frequency. Now there is this graph between displacement and time. So this is your graph between xt, graph of damped simple harmonic motion, that is displacement time. We have done in pretty detail about velocity time graph and acceleration time graph and displacement time graph for simple harmonic motion, and not for damped. So in damped, if you see, the amplitude actually keeps on decreasing, so it will keep on going like this, okay, and the amplitude is going to die, the wave is going to die, the vibrations are going to die. Now the cost term in my equation of solution, in the cost term actually provides me the wavy nature, and this term, the negative side of e raised to minus bt, will provide me the decreasing amplitude. That's the reason why you see, okay, this orange graph represents e raised to minus bt by 2m, and this cos actually provides me the wavy nature, because cos ka value keeps on repeating between 1 and minus 1. And last but not least, we have this thing called as a note, where many boards can put you an MCQ on that, or a very objective type of question, that damping actually decreases the amplitude, which is pretty visible, but it increases the time period. So the time period is increased but the amplitude keeps on decreasing. So this is a note kind of stuff, and just remember that damping decreases the amplitude and increases the time period. So this is what it is for today's video. We have finished off today's video. Thank you so much for watching. If you are still with me, subscribe the channel in case you have not done so yet, and keep watching the videos in a link. Watch from the playlist. There are other chapters as well, and have a nice day. Thank you. Bye.